brittle material can withstand higher compressive stress, cannot take tensile stress. Okay, there's no such thing in shear. Right. So the next thing that we are going to look at, so if we're going to draw this in 3D, okay, we're going to draw this in 3D now. How does it work? Okay, so now I'm going to sketch a 3D element. So this is our X, Y, and this will be our Z. Okay, so I'm going to draw the shear. Okay, what does it look like in 3D now? Okay, so I'm going to go on. So my element in 3D now. So we already know that this and this is shear XY, and over here is shear YX. And then I'm going to draw another two. Right? So this is shear. The intersecting plane is Z. The shear direction is in Y. And then over here, the intersecting plane is Y. The shear stress is coming in this direction, which is our Z. Okay. And then another one to draw, which is this way now. So this is shear, the intersecting plane is X, and then it's flowing in the Z direction, and this is shear, the plane is intersecting the Z axis and it's moving in the X direction. Okay. And one thing is for sure is always the fact that shear XY, regardless whether is it 2D or 3D, okay, and shear ZY is equal to shear YZ, and shear XZ is equal to shear ZX to achieve equilibrium. If not, right, the element will start to rotate. Okay, so you have to achieve what? Equilibrium. Okay, right. So let's look at failure. Now, what I'm going to explain next is pretty abstract. Okay, and I'll tell you why it is pretty abstract. Why it is. Okay, so let's look at failure. All right, failure due to shear force. Okay, due to shear force. Okay, let's look at failure due to shear force. So if we have a cantilever beam, okay, we have a cantilever beam, and then we have a beam built in, which is what we call cantilever. And let this beam have layers. Okay, I will have layers. One layer here. All right. And we are going to have a force P over here. And the P is also equal to V, where V, right, is the shear force. And if I were to draw our transformation, this is X and this is Y, right? The shear force or the shear stress will be pushing this down here. So I'll use a different color. Right? So you know that this is shear, right? The intersecting plane is X. This will go up in Y. Okay. And we know to achieve equilibrium, there is a counter, right, moving at this direction. And hold on, did not work. And it's moving in this direction. And this is our shear YX. Okay. Now we have to get this concept right. Okay. So the next thing that I'm going to ask you, which is yeah, this is pretty weird. Okay. Is failure, okay, where the question I'm going to ask is this: where is failure going to occur? Right? Is it going to occur on the plane intersecting the x-axis, or is it going to fail on the plane intersecting the y-axis? Right? Anyone want to make a guess? Is it going to be on the plane intersecting the x-axis or the plane intersecting the y-axis? Anyone? If you just look at the shear force vertically, you will easily say it's going to fail, right, on the plane intersecting the x-axis. Okay. So I'm going to shade this in. I'm going to shade this in yellow. Okay. And then I'm going to shade this in green. Okay. That is, yeah. So I will show you, or I will try to convince you, right? The failure, the plane where failure will occur is intersecting the y-axis, or highlighted in green. Okay, not in yellow, which is interesting. Okay, not in yellow, but the one in green. Why is that? Okay, so if this structure were to deform, okay, due to the shear force, okay, if this structure were to deform, so I will do this. Okay, this is how the deformation, or this is Yeah, this is as let me not be so exaggerative about it. Okay. Okay. So I'm going to cut and paste. Okay. Bear with me, okay. So this is the deformation pattern, as you can see. Okay. So as I said, these are all the layers. Okay. And this is what you will see. And if I were to, you can see here, if I were to amplify this region, I'll use a different color. If I were to amplify this region down here, right? If I were to amplify the this region down here, right? So I will draw it bigger now. Yeah, I'll draw it bigger now. Okay, you will see that there's a change or there's a slip occurring on this plane over here. There's a delta. There's also another what? Delta. Right? There's a delta. And this delta, the direction of the delta correspond to the what? Wrong. Correspond to what I'm highlighting in green. Right? So this is where the slip, yeah, this is where what we call the slip is parallel to the layers. Okay. And what you see at this height over here, or I'll use a different color now. This height over here, right? Geometry did not change, right? It did not change, right? So you ask me, Eugene, if that's the case, why are we calculating shear xy? Okay, so whatever we calculate shear xy is in that direction. Okay, is in the direction of the shear force. Okay, so the shear stress or the plane during or the plane used in the analysis is always parallel to the shear force. Okay? But failure will occur to the plane perpendicular to the shear plane. And let me shift this up. To the shear plane. right? So we always calculate shear xy. Okay, but the failure is always perpendicular.